Okay, welcome to lesson 22. So we're going to get to parameter estimation. So confidence intervals are a huge deal. Then the next few weeks we'll be doing confidence intervals as well as hypothesis tests for certain scenarios. Absolutely, this is something that we're going to carry with us throughout pretty much the rest of the quarter here. Okay, so a point estimate, it's our starting point. If I'm trying to calculate or estimate the mean for a population, the place I'm going to start is with the mean of a sample. It's my best guess given the information I have. So in general, you want to make sure that what you're using, it gives an unbiased estimate. So we have a tendency, like X bar is an unbiased estimator, like in the long run for the mean of the population. So we're going to show that when we have a question about the population. What is theta? So generic parameter value. We're going to take a random sample, calculate the sample version, so theta hat. Just a reminder, anytime you see a hat, that was calculated with sample information. And then we're going to tie it back to the population. If you don't have random sampling, you don't get the inference part, right? So if you don't have here, you don't have here. So unbiased, what we mean by unbiased is on average, when we use this estimator, we're going to get the value of the parameter that we want. So on average, it does a very good job. So X bar, on average, if you took all of the sample means you could, the average of all those sample means will be the population mean. So, for example, p hat is good for p, X bar is good for mu, S squared is good for sigma squared because they're unbiased. Okay, so we start off with our point estimate, and it's often a great starting place, but it's not in and of itself a great end place, right? The sample mean is almost never exactly equal to the population mean. There's some variability. So we put together a confidence interval. So we start with our point estimate plus or minus some amount. So we have an interval estimate. If I wanted to say, hey, the average for quiz 1 out of 70 points, I could say, oh, well, I took this sample of 10 people and it looks like the average was 68. Well, that's either exactly equal to the population mean or more likely it's not. It would be safer to say, you know what, I estimate that it's between 66 and 70. That would be a much, and I'm just making up numbers here, a much more reliable way of estimating. So it makes it so you're much more likely to be accurate. So it increases the likelihood that your estimation procedure will actually capture the value that you're interested in estimating. And so it gives a range of plausible values, so reasonably it would make sense the average would have, values in this range that is given. And at least the way we're going to do this in this class, the point estimate, it's always the exact center of the interval. There are instances where this is not quite true, but in this class it's always going to be true. So here's a basic, pretty basic example here. I went ahead and I decided to take a random sample from a normal distribution. I wanted to take a sample of 16 observations from a normal distribution with a mean that I'm not telling you right now, and a standard deviation of 20. So I'm giving you the information that there's 16 in the sample and that the standard deviation of the population is 20. I know the true value of sigma of x. So the idea is we're going to go ahead and try and calculate an interval and see how it does. See, hey, does it capture that true value? So when you take this sample of 16 from this population, we get ourselves a sample mean of X bar equal to 236.96. So we're going to use this information to try and estimate what mu of x is. So our starting point, it's going to be the sample mean. This is where we're going to start, and we're going to try and pivot from here. And we can guess that mu of x, it's somewhere close to 236.96. But how close? That is what we want to know. So things that we know about the distribution of x bar, we know the population was normal, so we know the sampling distribution is going to be normally shaped. We know that the center is going to be at mu, but we don't know this value. And we know the spread. So we know the spread is going to be equal to sigma of x bar, which is the standard deviation of the population, so that 20, divided by the square root of the sample size. This is nice. So it's 20 over 4 is equal to 5. So that will be the standard deviation of the sampling distribution of x bar. So here we're going to have to use a little bit of just kind of go with the logic here. We know it's centered at mu of x, but we don't know where it is. And if you remember from that empirical rule, plus or minus 2 standard deviations from the mean is roughly, approximately, the middle 95%. Right? So hopefully that's not too, remember that 68, 95, 99.7 rule. And I was calling it the empirical rule. I've heard it be called both quite often. So we're going to use this notion that wherever that true mean is, if you take within 2 standard deviations of it, that's roughly the middle 95% of all the sample means you could possibly get. We are hoping that the sample mean we observed, that 236.96, is one of them. We don't have any way of knowing for sure, unless you happen to know the population information. But, well, let's see how we do. So the idea is, if our sample mean is within 2 standard deviations of mu, we could also say mu is going to be within 2 standard deviations of the sample mean. So A is as far from B as B is from A, kind of idea. And thankfully, we know where the sample mean is, and we could calculate how far 2 standard deviations are. So we're going to go ahead, we're going to calculate the interval from basically x bar minus 2 times sigma of x bar to x bar plus 2 times sigma of x bar. And we anticipate that 95% of the random samples that we do this with will make an interval that has mu in it. So we're really hoping that we have one of the good, 95% samples. We don't usually get to know for sure. So here, we did this already. Sigma of x over root n. It's 20 over square root of 16. It's 20 over 4 is 5. So we want to figure out what's 2 standard deviations on either side of x bar. So 236.96, that's our starting point. So plus or minus 2 times sigma of x bar, that's just that 5. So 236.96 plus or minus 10. Yay, some math I can do in my head. So be careful here. So my interval, I do not have units here because this is a simulation from R. But if I had units, I'd want to include them. So 226.96. The smaller number goes on the left. Be very careful, it is an interval. So the smallest number, the number that is left on the number line has to go on the left. To 246.96. So what we're saying is, hey, our approximately 95% confidence interval for the mean, mu of x, it's going to be from, we anticipate mu of x is somewhere between 226.96 and 246.96. That is our interval here. So 226.96 and 246.96. So we can say we're roughly 95% confident the true population mu is somewhere in here. The idea is not that we're confident in the specific interval, but that we're confident in our interval making process. So if I took every single unique sample of 16 from this population and calculated a confidence interval this way, 95% of them roughly would have mu in them. So it's confidence in the process. So are you ready for what mu is? It's 240, which is in our confidence interval. So that means that we did a good job here. Our sample was a good sample. When we calculated a 95% confidence interval, it had mu inside of the interval. 240 is between 226.96 and 246.96. So this is good stuff. We're really bummed, and we usually have no way of telling when we get basically a bad sample that when we calculate the confidence interval, it does not have the true value of mu in it. We're not usually fortunate enough to know whether or not that's actually true, but it is a bummer when it happens because it means that our estimate's not very good. So constructing a confidence interval. So when we know that our sampling distribution of whatever sample statistic is normal, right there we were using that empirical rule. So we were saying, hey, roughly 2 standard deviations. If you're going to be more exact, the z-star of 1.96 is more exact. So 1.96 standard errors in either direction, not 2. 2 is a little bit bigger than 95%. So if I go ahead and I want to calculate it, it would be my sample statistic plus or minus 1.96 times the standard error for that particular statistic. And it will, so 95% of the time that I take a random sample and I calculate my interval this way, it's going to capture that true parameter, theta. So here is where the center bar is this true value of theta. If you look, this is my first sample. Here's my point estimate. Yes, theta is right here. So you're basically looking here like, oh, look, there, theta is in my interval. Theta is in my interval. Here it is. Here it is. You'll notice every once in a while you'll miss. Roughly 5% of the time, if you're doing a 95% confidence interval, you're going to miss. It's not ideal, but, and you can do things like increase your confidence, but there is a trade-off, and we'll talk about that. So we can be 95% confident the parameter is captured by the interval estimate. However, do know that about 5% of the confidence intervals calculated this way from random samples of whatever size are not going to be accurate and capture data in our interval. We aren't lucky enough most of the time to know if we have one of the good ones. So the structure of a confidence interval here, they're all going to have pretty much the same general form. So our point estimate, so this, if we're doing a single mean, this will often be x bar. If you're looking at proportion, it'd be p hat, that kind of idea. Critical value, so far we had z stars. Next week we'll introduce t stars, but your critical value is going to be z star or t star. Just know that's something for next week. And standard error, so something about that spread. So you have your point estimate, and everything after that point estimate, you could call that's your margin of error. So plus or minus, everything after that, that's your margin of error. So be careful. We love to give you an equation here and say, oh, what's the margin of error? Oh, what's the standard error? Oops. Just note that margin of error is different than standard error. Standard error is part of margin of error. But margin of error is the product of the critical value and the standard error. So here, the standard error is a measurement for the variability of the estimate. So we want to know from sample to sample, how much does X bar vary on average from sample to sample. And then here's so for a 100 times 1 minus alpha % confidence interval, which sounds much fancier than it is. We'll explain a little more on the next slide. The critical values that we use for Z-star, at least this week Z-star, are going to be the alpha over tooth and the 1 minus alpha over tooth percentiles. I'll show you what the heck we mean by that. So I'll show you that the Z-star will have. So, oh man, I think it's it. I promise, there is a slide. I thought it was the next one though. So confidence and confidence intervals. So we start off with a question about the population. Hey, what is the value of theta? We take a random sample repeatedly, and we calculate the sample version, theta hat, repeatedly, and we get a confidence interval every time. So just doing this process repeatedly, everybody takes a random sample, they use it to create a confidence interval. 90% of those intervals, roughly, will have intervals that have the true value of theta in it. And so roughly 9 out of 10, or 90%. And roughly 10% of those intervals will fail. So if we're making a 90% confidence interval, that means that roughly 90% of the random samples we take and the confidence intervals we make from them, roughly 90 will accurately capture theta, and about 10% of them will inaccurately capture theta. So like here, all of these ones with the gray captured, but then this one in the green, it missed. You don't like to miss. You want to miss as little as possible, ideally. But there are definitely trade-offs in order to make sure you do miss less. So here's that slide I was talking about. So if I want 90% confidence, 95% confidence, alpha's 0.05. So I'm going to want the 2.5th percentile and the 97.5th percentile. So what it comes down to is you want the middle 95%. Right? So you want the middle 95% of this distribution, which means I still have 5% out in the tails. But since it's perfectly symmetric, I need 5% in each of the tails. Not in each of the tails, but divided by the tails. So 0.025 is 0.025. Did not leave room there. So the idea here is if I have, looks like 2.5% here, this is my 2.5th percentile. And the Z-star for that is negative 1.96. And here, this is 2.5% here and 95%, so this is my 97.5th percentile. And there's only 2.5% above it, so percentile, the Z-score here, or Z-star, is positive 1.96. I can do something similar for the 90%. So here you want the middle 90. It's going to be something like here. I'm eyeballing it. So the middle 90%, which will mean that you have 10% left over. So you've got 90 in the middle, but you've got 10% at the edges. You have to divide that by 2 because the area has to add to 1. So if there's 10%, divide by 2. That's 5% in each tail. The idea here is 5%, 90%, 5%, they add to 1. So if there's 5% here, this is my 5th percentile. I have 5%, 90, so this is my 95th percentile. Things to note, if I did subtraction, so 95th percentile minus 5th percentile, I'd get 90. Oops. So if you do subtract your percentiles and you don't get back to whatever's supposed to be in the middle, something's gone sideways. And so once I have those percentiles, we do have the z-scores, the critical values for that. Z could be negative 1.645. Don't want that even with the... And this will be z star is equal to positive 1.645. And it kind of becomes like a moot point, like with the plus or minus, you could use either one of these. Just make sure that when you put your interval together, you put the smaller number on the left, the bigger number on the right. We will hone right in on that if the order is out of order. So 99%, hopefully this is getting a little hat. Now you have the middle 99% in here, which means there's 1% left over. So you have to divide by 2, so 0.5% here. So this is my 0.5th percentile. My z star is negative 2.576. I am not just pulling that out of my head. I happen to have my z stars memorized for 90, 95, and 99% confidence. Those are pretty much the 3 people tend to use. You're not expected to memorize it. I would have it written somewhere though. You need to be able to use it. So this is going to be 99% plus 0.5%, 99.5th percentile. And my z star is positive 2.576. So that's how those are calculated. I find that a little easier than the abstract, like, oh, it's 1 minus alpha over 2, but absolutely you can plug that in. So once we've decided we're doing an estimation problem, so this will be like researchers want to estimate. Oops. Or what is the value of blank? That kind of, it's an open-ended question. They want to know, hey, what is the value of this? You wouldn't answer this question with a yes or no. You would answer this question with a number or a range of values. So we're going to go through these steps a few times throughout pretty much the rest of the term. The first thing is to state the question of interest in context. So we want to say, oh, well, what is the average tuition cost of all OSU students? Something like that. Identify the parameter you're interested in. Is it a mean? Is it a proportion? So 1, 2, or more populations. This week we're going to stick to 1. Next week we'll up to 2. If the variable you're collecting is categorical, you should be looking at proportions. If the variable you're looking at is quantitative, you should probably be looking at means, occasionally medians, but we won't actually run those tests. But things to know, like we're going to want the notation as well as in words, like what does that stand for? State the confidence level. So if it said, hey, calculate with a 99% confidence, say 99% confidence. We're going to have some conditions we need to meet. So we'll have conditions this week, and we'll have some slightly different conditions next week. The conditions are pretty much the main difference between the different procedures we use. Like if we don't meet the conditions for the Z procedures we use this week, we have a new set of conditions to meet for T procedures next week. Calculate the actual interval, and then this one's huge. You have to actually return to the question and answer it. So you have to say, okay, well, with whatever percent confidence, we estimate the average OSU tuition in spring 2020 is blank to blank. That kind of idea. And we do have, we have a template for that. So here's the template. Super important. Like, we'll have a template for this and a template for the hypothesis test write-up. This is super important. This is our two-part write-up for a confidence interval. So we'll say the confidence interval for the blank % confidence interval for the, usually we have a mean or proportion. It could be a difference in mean. It could be a mean difference. And then you need to write what your variable is in context of your population in context. And the context is so important. Is on average estimated to be between whatever your lower bound is with units and your upper bound with units, with a point estimate of your point estimate with units. So this is like X bar from your sample, or P hat from your sample, whatever you actually saw from your sample. And we will use this template moving forward. We will stick to it a lot. Anytime we say, hey, give us the two-part conclusion for a confidence interval, this is what we mean. And we'll have a two-part conclusion for the hypothesis test as well. So choosing confidence levels. So I mentioned 90%, I mentioned 95, and I mentioned 99. So it's a trade-off of precision and accuracy. So the most common by far are 90, 95, and 99%. Every once in a while someone will be like, oh, look at me in my 98% confidence interval. And you're like, oh, cool. Like, you don't know why because it's weird, but some people do. And it totally depends on the norms in people's fields. In general, the wider the interval, well, not in general, if the greater the confidence. So you increase your confidence, you increase how wide it is. Because you're basically casting a bigger net in order to be more likely to actually capture the value of the parameter. So here are same point estimate for all of these. Here's a 90% confidence interval, here's a 95, here's a 99. So if I increase my confidence, it gets wider and wider. I have my point estimate, which is extremely precise because it's a single point. However, it's not accurate that often, right? You're either exactly right or you're wrong a lot of the time. And then on the other end, if I basically include all possible values, it's accurate, like you're 100% guaranteed to be correct, but there's no precision, and that could be very unuseful. So, for instance, if somebody asked me, hey, Kelsey, what was the average quiz 1 score out of 75? And I said, well, the average with 100% confidence was between 0 and 80 points. It would be kind of like a, well, duh, thank you for not being useful at all. Kind of, it's such a wide interval, it's not useful. So you don't want to be too wide of an interval that you aren't useful, but you don't want to be so precise that you're not accurate either. So it's absolutely a trade-off. 95's the most common one, but a lot of times that's just because folks in certain fields are used to using 95. It's not necessarily for some sort of scientific basis that they're making that decision. So yeah, compared to the 95 as the baseline, more precise, less accurate. The 99 is more accurate, less precise. 95 is relatively accurate and precise. So when we want to calculate a confidence interval for mu, and we know sigma from the population, and just know that this is not that common, we can use this setup to calculate a confidence interval. So you want to estimate the value for mu for a single population. So we do have conditions. And a lot of these conditions are going to be pretty regular for us. condition 1 in particular is pretty much always going to be there. We're always going to want to have a representative sample, because if our sample is not representative, pretty much everything we do afterwards is really questionable. So our second one, it's saying, hey, our sample size is big enough that we know the central limit theorem is going to kick in for the distribution of x bar, the sampling distribution of x bar. So we know that the sampling distribution of x bar is going to be roughly normal. And then this one, it's going to change. So condition 3, it's only true when we're using these z procedures. And that's when we get to use z star. If you know sigma, you get to use like z-scores and z-stars, but most of the time we won't. So if we happen to know the population standard deviation, sweet. And when we do, we can go ahead and we can say, oh, well, my confidence interval, it's going to be x bar plus or minus my critical value is z star times sigma of x bar. And sigma of x bar is just that sigma of x over root n. So my z star is the critical value, and this sigma over root n, that's my standard error. So what's great is throw back to those z stars that we had. Well, actually, no, these are more specific. So anytime I want a 90% confidence interval and I know sigma, I can use these z star values. So I can use 1.645. I'll use 1.96 for 95. 2.576 for 99. So that's just from here. And absolutely you can use R to find these values. Technically these values are rounded a little bit, but these will be, honestly, if we do hand calculations, these will be the values we use most of the time. Okay, so when I have precise, when I'm talking precision here, I want to refers to like narrowness of the interval. So how narrow does this interval get? Accurate refers to how often the intervals will accurately, capture value of theta. So the more accurate it is, the more likely that we have an interval that actually captures the value we're interested in. The more precise it is, the narrower that interval will be. We love it, absolutely love it. That's our happy place when we can get both. So 95% confidence is in the middle. It's the most commonly used one. It's a compromise of the other two. It's relatively highly accurate and relatively high precision. The 90%, so if you see the z-stars, as they get bigger, the confidence goes up because they're making the interval wider. But it does come with that trade-off that, like, if you go to a 99% confidence, it's definitely more accurate because it's wider than the other two, but it is less precise. And some people, they won't appreciate it if they said, hey, what's the average? And you went, oh, the average was between 30 and 80. Well, that's not a very narrow interval, depending on, like, if it's for that quiz, that's definitely not a narrow interval. So people tend to go with 95. In general, we'll give you a specific value. We'll determine ahead of time. So just to kind of note on precision, so in general, so as precision's going up and accuracy's going up, this is our happy place. We love to be accurate and precise. This is a target, so you're hitting the center of the target, and it's really precise, like they're really close together. You can be really precise and inaccurate, so like I'm missing the center, that doesn't make us as happy. That's not a great place. And then definitely this is our sad place when you're not accurate and you're not precise. So you're missing the mark, and it's a wide interval. It makes us very sad. And then this one, it's accurate, but it's not very precise. Like it's not the tight grouping that you saw in the first one. Precision in general, you can increase precision by having a larger sample size. Accuracy, you have to do as much as possible to eliminate or at least minimize the biases. So you have to try and make sure that you don't have sampling bias. You don't want to be using a volunteer sample or convenience sample. You have to try to do everything you can to reduce the response bias. So you want to make sure the wording on a survey is as neutral as possible, that the answer options are reasonable, that kind of idea. So in general, you want to obtain an unbiased sample by taking a random sample, and there are different kinds of random samples, and then control for things like the wording of your question, consistent measurement tools, etc. Okay, so here's our example, and we'll use this one a little bit, I think throughout the rest of this one. But so we have an ecologist. They have this river, and they're really interested in the zinc concentration in this particular river. So they go ahead and they randomly select, I'm not sure how, but they randomly select 36 locations on this river, and I don't know how big they are. And they find the average zinc concentration in those 36 locations. It's 26 grams per milliliter. And it is known, I want to really highlight this. It is known. In general, if we say it is known, whatever follows this part of the sentence is about a population. So it is known that zinc concentrations vary on average. This is talking about a sigma. This is sigma of x here. So super important to note. So zinc concentrations on average vary on average 0.3 grams per milliliter. So x, this is just your zinc concentration. Oops, I can spell sometimes. Concentration of location. So it varies from location to location. So find the 95% confidence interval for the mean zinc concentration of the river. Okay. Well, you know what? I might go through these steps here. So step 1, my question. So here we're asking an open-ended question. We want to know what is the average zinc concentration. So what is the average or mean? We're okay with you using either one here. Zinc concentration. So that is my variable of interest we're collecting. And then I have to say of my population, so of all locations on this river. So that's my question. Step 2, my parameter of interest. So I'm interested in mu of x. So this is my notation, and we will do this. We will say, give us the parameter of interest in notation and in context of the problem, like in words. So this is the notation, it's mu of x. And then the description comes. So if you word this right there, pretty much everything after the what is, that right there is my parameter of interest. So what is the average zinc concentration? So I'll even write mean zinc concentration of all locations on this river. So things to note, here we also do like inventory. So this is grabbing the information we know. So, let me see here. I know that I have 36 locations, which is very conveniently a square. Just throwing it out there. The average of those 36 locations, so that's X bar, is 2.6 grams per milliliter. I'm not dropping my units. And then we have sigma of X is 0.3 grams per milliliter. Step 3, I want to state what confidence level I'm using. Looks like 95%. So 95% confidence. Oops. So I'm going to write here, oh, my Z star, my critical value, it's going to go ahead and be for 95%, 1.96. Step 4, I need to check my my conditions. I'm going to number them the same as they are on the other page without writing them all out because there's not really space here. So 1, is it a representative sample? So it's asking, did we take a random sample? Yes. So that looks good. 2, is my sample size going to be big enough? My sample size is 36. That's higher than 30. So yeah, central limit theorem will kick in for X bar, for the sampling distribution of X bar, because N is 36. And then 3, do we know sigma? Yes. Sigma is that 0.3 grams per milliliter. So I've met all my conditions. Sorry, I know that it's getting a little scrunched up in here. Ideally, I would have spread this out over at least 1 or 2 more slides. So step 5. Now we're going to do the calculating. So X bar plus or minus Z star times sigma of X over root N. I have everything I need to plug in there. So X bar is the mean from the sample, so 2.6 grams per milliliter. Plus or minus, it's a 95% confidence interval, so my critical value is 1.96 times sigma, which is 0.3. Oh, that's so nice, over root 36. Here we go. That's not math I tend to do in my head. So I end up getting, oops, it's equal to 2.6 plus or minus 0.098. Remember to put the first, the lower number first. So my 95% confidence interval for mu, it's going to be 2.502 grams per milliliter, because I need to include my units, to 2.698 grams per milliliter. So here we are. You might have gotten a sneak peek. The next slide, now we're going to write it up. Now we're actually going to return to this question in step 1, and we're going to actually answer it in that format that we had on that. I don't have the correct slide written down here. Seriously though, that one that I started, that slide with the format, absolutely have that written somewhere. That absolutely is going to come back repeatedly, not just this week, but in pretty much every week from here. So here's my confidence interval. I cheated and put it there to help me out. So now I want to go ahead and write this up. So the 95% confidence interval, I honestly think that this particular blank is the easiest one to fill in. For the true, note that when we put true, we're usually talking about like a population parameter. We're not going to ding you if you use the word true, but just know that when we use the word true, we're specifically talking about a population parameter. So for the true mean, and then mean what? Oh, zinc concentration. The mean zinc concentration of what? So now we have to put our population, so of all locations on this river. On this river. Is on average estimated to be between, so I'll put the lower one first with units, 2.502 grams per, I did not leave a lot of space there, milliliter, and 2.698 grams per milliliter, with a point estimate of, so this is saying, hey, what was the sample mean from that original sample? 2.6 grams per milliliter. So we're going to be looking for every single one of these things that I filled in the blanks. I'm going to absolutely look for the percent confidence that we use to calculate the interval, that we used it to calculate an interval for a mean, the variable of interest in context, the population of interest in context, and then the interval itself with units, and then the point estimate from the sample. We will have a checklist every time, and we will look for all of those things. If you have a very reasonable way of reordering the sentence because it absolutely doesn't make sense this order, okay, but just know that we will have a checklist and we will look for every single one of those things. We are a little finicky with how I've seen we are blank percent confident, the 95% confidence interval for this with 95% confidence. You do have to make sure that the wording here, it does have to say 95% confidence in there somewhere. We do tend to be pretty picky. Like, you cannot take stats terms and put it in a thesaurus. We will immediately go, no, this is not the word we use. We are very finicky about some of our wording, so just keep that in mind. So one other thing, calculating a sample size. So this is a scenario, someone has an idea like, I want to make a 95% confidence interval for the mean zinc concentration at this river, but I want it the interval to be no wider than this amount. So they have an amount in mind, and a confidence level in mind. You can use this information to say, okay, well, what is the smallest sample size that you need to be able to take in order to ensure that your interval is no wider than so much. So here, specifically, instead of saying, hey, I don't want it any wider than this much, we'd say we want the margin of error to be no bigger than this. So we want to know, like, the margin of error, if you multiply the margin of error by 2, that's the length of your entire interval. So if you don't want your interval any wider than 5 grams per milliliter, you want your margin of error to be no bigger than 2.5 grams per milliliter. That's the idea. And so what we did essentially is we said, hey, margin of error, we don't want it any bigger than, so remember margin of error is sigma of x, I'm going to see z star times sigma over root n, and we say it's less than some amount. We are just solving to figure out what n will be. And just noting here, for a 1 minus alpha times 100% confidence interval, that's kind of a weird way to word it. Usually it's in 90%, but if we're doing 90, alpha is 0.10. If we're doing a 95% confidence interval, it's 0.05, 99, 0.01. You'll notice they add to 1, add to 1, add to 1. So there you are. Whoa, do we not have an example here? So guess what? I am going to stick one in here for the river. I want to have one. So zinc concentration example. And we don't want a margin of error. We want margin of error to be no bigger than, oh gosh, the handwriting is so bad, 0.04 grams per milliliter. So that means that when I have my interval, the entire interval is not going to be any wider than 0.08 grams per milliliter. That's how precise we want to get it. So, and I want to stick with a 95% confidence interval. So Z star is still going to be 1.96. All the values, this is from the river example, so sigma of x is still 0.3 grams per milliliter. And that's all we're going to need. So I want to figure out how big of a sample size do I need. So note, if you go ahead and you calculate the sample size, you are going to want to round up. And I'll get there, I'll poke at it when we get there. But note that you don't want to take samples of like half. Like you can't sample half of a person. So you're going to need a whole number value. So let me set it up real quick. So Z star times sigma over margin of error squared. I'm going to just focus on this part first. So 1.96 times 0.3 divided by 0.04. Square that. I'm going to get 14.7 squared is equal to 216.09. So things to consider, you can't sample exactly 216.09 locations. You can only sample an exact number. So if you round down, 216 is not enough because you get n is greater than 216.09. 216 won't be enough. So you must round up. With sample size calculation, always round up. So sample at least 217 river locations. So we need to take a sample of at least 217 river locations to ensure that we get a 95% confidence interval that is no wider than its margin of error being 0.04 grams per milliliter. So I want to make sure we had an example. I'm sorry, I thought it had its own slide. But always remember to round up. And I believe that's going to be our lesson 22. Thursday, we're going to get onto hypothesis testing. These are very, very different concepts. They have some similarities, but I really want to make sure they're introduced on different days. So we'll see you there.